Okay, good afternoon. Shortly, we will hear an interesting lecture by Professor Ben Ezra on the exciting world of silicon photonics. Our scientific journey will start with silicon photonics devices and end with high-performance computing, high data speed transmission, silicon photonics, and more. The photonics industry is a worldwide technological and economic growth engine. It contributes to the Israel economy about $6 billion annually. This webinar is part of an enlightening series organized by Photonics Israel, exploring diverse facets within the field of photonics. Our mission is to enrich photonics knowledge, fostering collaboration not only within Israel, but also with photonic entities worldwide. Photonics Israel is sponsored by ISORAD and works close cooperation with its subsidiary, the Israeli Center for Advanced Photonics. Since we started, we have established close relationships with similar clusters in the US and Europe. My name is Shlomo Glazer, and I am the manager of Photonics Israel. Professor Yosef Ben Ezra received his PhD from Tel Aviv University. He's working on the non-DSP, pluggable, and co-packaging transceivers, developing non-invasive method for calibration, and monitoring integrated and programmable photonic systems. Professor Ben Ezra has made significant contribution to the field, co-authoring more than 100 papers that have been published in prestige international journals and presented at conferences. His expertise, his expertise spans semiconductor physics, nonlinear effects, and optical communications. In addition, he is the author of 15 scientific books, chapters, and 50 patents. Question and answer will be at the end of the lecture. Please post your questions on the chat tab. I wish you all a pleasant and useful listening. Professor Ben Ezra, the stage is yours.
Okay, thank you for the introduction. Good evening. I will start my presentation. Actually, the presentation consists two main parts. As Shlomo mentioned, I'm working at the Holon Institute of Technology, and also I am CTO of New Photonics. So the first part will relate it to the silicon photonics, to the integrated photonic circuits, needs, technologies, trends, and etc. And after this, I will present some results from New Photonics in the field in order to give you a better understanding what we can do with photonics. So what is the definition of photonic integrated circuit? It's a very simple definition, and you can see on the slide it's integration of optical functions on a chip. The main question, okay, so we can integrate optical functions on a chip. What kind of problems we want to resolve? We need these photonic integrated circuits, and what are the advantages to introduce and to use these photonic integrated circuits. I think that during this webinar, you will have a better understanding what kind of problems we want to resolve with the photonic integrated circuits, what are the main challenges related to the technology, and I will give you some applications and examples of the technology. Today, photonic technology is considered as a disrupting technology for multiple fields. And those fields include optical communication, interconnect, AI, which is recently growth and pushed with the GPT, and quantum computing, which also is progressing, and the photonic integrated circuits are considered as a good candidates for the quantum computing and quantum communication. I will try to give you the whole picture, what are the main drivers of the photonic integrated circuits, and I will start with this slide. It was published recently by NVIDIA, light counting. NVIDIA needs 32 more bandwidth. When they are talking about 32 times more bandwidth, what they are meaning? Today, all communication in data centers is based on 112 gigabit per second per lane communication with PAM4 signals. That means that each symbol transmits 2 bits. So the real need is 32 times. How we can achieve these data rates. And you can see the existing solution in the market, and you can actually pay attention that the green part is the optics, and the gray part is traditional electronics, including fast analog circuits, including digital signal processors, and etc. So the main functionality of the optics in these applications is just for at the front end of the device for the transmission of data via the optical fibers, but for the next solutions, in order to achieve 32 times more bandwidths, the functionality of optics is about 15% of the entire solution. And if you are looking to the power consumption, the main power consumption of those devices, of those transceivers which are transmitting 112 gigabit per second, is related to those electronic devices. So the main problem that we are facing, that the data rates are growing. We are looking at for higher data rates, 32 times more, and it will very, very difficult to achieve these data rates with the same approach. So we have to change something, and this change is coming from the integrated photonic circuits. Recently, there are some progress. We can replace those electronic devices, which are actually the bottleneck of the industry, because in order to achieve higher data rates, you need fast A to Ds, D2As, and DSPs. These DSPs actually takes more than 60% of the power consumption of those transceivers. So in order to achieve these higher data rates, it's almost impossible to put these standard electronics in the same footprint, which is shown in the middle of the slide. So integrated photonics can resolve this kind of problems. In addition, integrated photonics can be used also for biomedical imaging, for the communication in data centers, environmental sensing, and also for optical communication, even for the long haul communications, because also for the long haul communication, the data rates are increased, and industry is looking for more efficient solutions for optical communication. This demand actually pushed the market, and the estimated market in 2028 for the silicon photonics is more than $5 billion. And the main part of this market is related to the optical communication, in the data centers, but there are also other applications, and I will describe them, such as lidars or sensors or AI accelerators. They are also penetrate the markets, and it leads to growing the entire market of integrated photonics. You can also see the publication from September 6, 2023. TSMC is a huge player on the market, and they figure out that the silicon photonics is the next technology which will lead almost all critical solutions, and they are investing a lot in this technology. Actually, this publication is very important because it's actually give us a very good evidence that the big players believe that the integrated photonics and silicon photonics especially should be considered and should be the solutions based on those technologies should be penetrated to the market. Before I'm going to the applications, I want to very briefly explain what are the main components of the integrated photonics, what are the limitations, to give you the better understanding of the limitations, performances, and etc. The main photonic component in integrated photonic is the waveguide. Why waveguide? Because it can guide the light, and it is crucial if you want to connect several optical devices. As it was mentioned in the first slide, it's an integration of optical functions on a chip. So in order to integrate those photonic devices, we need the waveguides. Otherwise, we cannot guide the light from point to point. There are different structure of the waveguides, but what I want to give you just the understanding what is actually the silicon photonic wire, silicon waveguide. You can see that the silica substrate and the silicon waveguide on the top, approximately those are the dimensions, 500 nanometer width, and the height is 20 nanometer. And it depends on the geometry of the waveguide. You can achieve relatively very small losses. This is in C-band. C-band is considered from 1530 till 1560. The losses are less than 1 dB per centimeter. So this is a very interesting result. And if we are going to the different foundries and different PDKs, and I will introduce those foundries and PDKs in continuation, all they have the similar solution. The losses in silicon is about 1 dB per centimeter. There are other technologies based on the silicon nitride. In silicon nitride, you can achieve approximately 1 dB per meter and maybe less. So there are different technological platforms. And if you are looking, for example, for the solution for quantum computation, quantum communication, where losses very important. So instead of using the standard silicon technology, you can use the silicon nitride. But those are numbers. And actually, you need also other passive photonic devices in order to split or combine the light. And this is actually schematics or some geometry of those passive optical components. You can see a standard Y junction, A, or rib directional coupler, or MMI, there are different components in order to allow you to design the entire system. Also, you can see an array of waveguides. This array of waveguides is used in optical communication for WDM, wavelet division multiplexing applications. As you can see, it's a filter bank. You can actually combine and split different wavelets. You can design this AWG, this array of waveguides at the central wavelet you are looking for, with the spacing you are looking for, etc. Also, there are some kinds of couplers in order to enable the integration of photonic circuits with the laser source, light sources, or with other photonic chips. So this is the example of the grating coupler. There are other types of couplers, so as H couplers. There are a lot of possibilities to how to connect the photonic integrated circuits to the light sources, or how to integrate them with other integrated circuits. The next very important component in integrated optics, silicon photonics, or other platforms is the electrical to optical converter. Because without the conversion of electrical information to the optical domain, you cannot do a lot. So this is considered the main component. There are different physical mechanisms for this conversion from electrical domain to optical domain. And you can see in the table the comprehensive analysis of those modulators. The dominant part, the majority, is based on the PN dopants. It's a free carrier plasma dispersion. The structure is relatively very simple. You have a silica. On the silica, you have a silicon waveguide. And in the silicon waveguide, you have P and N dopants in the waveguide. And actually, you can operate with this device as a modulator, as a part of, for example, Mauser modulation structure. And what is the physics? Actually, if you will use the reverse bias to this PN junction, you can affect on the concentration of the free carriers in the waveguide. The concentration of the free carriers is directly related to the refractive index of the waveguide. So you can manipulate with the refractive index of the waveguide. You can use also the forward bias, but in the case of the forward bias, you are injecting a lot of free carriers in the waveguide. This definitely will increase the related losses of the device. So mainly those PN junctions are used in the mode of the reverse biasing, and there are different structure of those devices: carrier accumulation, carrier injection. With those devices, you can achieve very high bandwidths. Today, the achievable bandwidth with this kind of modulators is about 1560 gigahertz. The losses related to those modulators is about 6 dB. There are also other physical phenomena related to this electrical to optical conversion, like Franz-Keldysh phenomena or quantum confined Stark effect. It's Franz-Keldysh phenomena if we are talking about the bulk semiconductor, and if you are talking about quantum wells or quantum dots, it's the same phenomena, but the name is the quantum confined Stark effect. What is a Franz-Keldysh effect? It's very simple to understand. In semiconductor, you have the conduction band and valence band, and you have the gap between them. If you are applying the external electric field, you are changing the structure of this gap. And as you can see in this case, the photon has not enough energy to generate whole electron-hole pairs. But if you will apply the electrical field, it can be possible. So it means that you can manipulate with the absorption coefficient of the semiconductor as a function of the applied field. So independence of the applied field, you can increase or decrease the absorption of the device. So you can convert the electrical data to the optical data. There are also other physical phenomena such as Pockels effect, which is in lithium niobate or barium titanate materials. It's actually a dependence of the refractive index of the material on the electric field. And you can see this comprehensive analysis. PPA is a performance, power, and area, because the footprint of the device is very important. I will show you on the next slide what are the differences between the different types of the modulators. So free carrier plasma integration in commercial CMOS technology and foundry is very easy, because dopants is very basic in CMOS technology. By means of reliability, you can achieve a very high level of reliability. The thermo optic, it's very easy. It just requires a usage of the waveguide, and on top you can see you can put just the metal layer, but it's very low. You cannot achieve high data rate operation of this kind of modulators. It actually will allow you to change a few kilohertz and megahertz, but using this free carrier plasma dispersion of Frank-Keldysh or quantum confined Stark effect, you can achieve the huge bandwidths up to 50, 60 gigahertz. The same with the lithium niobate. With lithium niobate, thin film lithium niobate, there are some reports that you can achieve more than 100 gigahertz of operation. But you know, if you are comparing different parameters, each of these possibilities can be considered as a best alternative for your system, but you have to understand very good what is your application, what are your main limitations, and choose the appropriate technology by means of the complexity, reliability, footprint, cost, manufacturability, packaging, etc. So there are a lot of parameters you have to take into account. For example, this is the one of modulators, electrical to optical converters, so-called ring resonator. The ring resonator actually is a p-n junction. The shape is like the ring, so it's very sensitive to the frequency. The transfer function is a notch function. The device is relatively very small, 30-50 micrometer at all. And with these devices, you can achieve a very high bandwidth. What is the disadvantage of this device? It's very sensitive to the temperature. So the temperature stability of this device is the real issue. Electroabsorber modulator, it's actually based on the Frank-Keldysh effect. It's very small, 150 micrometer, and you can achieve also higher bandwidths, up to 60, 70 gigahertz. This is the footprint of the traveling wave Mach-Zehnder modulator. The physical phenomena is the same physical phenomena related to the plasma effect, but the length of the device is very large. 1 millimeter, actually, if you want to achieve a very low operational voltage, so-called V-pi, this is the voltage required to change the phase of the light by pi radians, and industrially applicable values is about 2-3 peak-to-peak V-pi. You need longest device is from 1 millimeter up to maybe 2 millimeters. So the footprint of this device is very large, but by means of the stability, sensitivity to the wavelength, this device is very advantageous than other devices. Okay, so we have the waveguides. We know how to guide the light in the integrated photonic circuit. We know how to convert the electrical data to the optical data, but finally, we need to convert optical data to electrical data. For this purpose, we need the photodetectors. At the photodetector side, they are very good news. There are a lot of existing solutions in silicon photonics, in indium phosphide. More of them demonstrates very high bandwidth, at least 70 gigahertz bandwidth with very good responsivity, because responsivity is the ability of the photodetector to convert the optical data to an electrical data. So actually, if you are using 1 milliwatt of optical power and you have responsivity near 1, this means that you will convert this 1 milliwatt optical power to 1 milliampere of photo current. The dark noise of this device is also very crucial, because in communication for the sensing purposes, we require very low level of the noise. And one of the components of the noise is the dark current, in addition to the thermal noise, which is related directly to the loading devices. You have resistance, etc., but the dark current is a very fundamental characteristic of the photodiode. Today, we have photodiodes with very, very low dark currents, and the operation is about 1-2 volt of operation. So we have a lot of solutions for the photodetectors. Okay, so we know how to convert electrical data to optical, how to receive and convert the optical data back to electrical data. We know how to connect between those devices. What is the missing part? The missing part is light source, because integrated photonics is related to the photonics. And if you have not a light source, you cannot do photonics, not communication, not sensing, not computation. So definitely we need lasers. The main disadvantage of the silicon photonics, that, as you understand, in silicon photonics, you cannot create the light source. So you have to use external light source. There are other platforms for the integrated photonics, such as indium phosphide. In indium phosphide 3-5 semiconductors, you can create the light sources, so you can monolithically integrate the light source with other optical devices, such as modulators, such as photodetector, waveguides, and etc. But if you are talking about the silicon photonics, even it's silicon or silicon nitride, you need definitely the external 3-5 semiconductor-based light sources. There are different technologies for the integration. For example, A is the integration by using the free space optic. This is a laser, this is a fiber, and this is a photonic integrated circuit. In this case, it's edge coupling. It's doable. Actually, when you are designing your photonic chip, you have a few options. You have grating couplers, you have edge couplers. This is the part of the PDK or library of different vendors, so you can even develop these couplers with your requirements. It's very simple type converters. If you have the basic knowledge in optics and in photonic design, you can easily develop this kind of device. what is the advantage of this coupling? It's relatively easy, but I will show you the comprehensive comparison between the different techniques, and nothing is, there is no free lunch. So maybe it's easier for the integration, but the related losses are relatively high. I will also show some link budget analysis in order to understand how we are very, very sensitive to those losses. The other type of the integration is a hybrid, so-called 2.5D with free space optics. So we have the photonic integrated circuit. This is the grating coupler. You have some pedestal. You can put your laser, and actually you can using this prism optical device, you can launch the light from the light source to your photonic circuit. In this case, it's relatively hard to achieve the wideband connection, and the related losses are also very high. The other type of the connection is the photonic wire bonding. So you can use the real fiber from the laser and connect to the photonic integrated circuit, or via the grating coupling, or via the edge coupler. More advanced techniques are related to the hybrid flip chip transfer printing, or heterogeneous, or even the monolithic integration. Some of foundries supports at least D and E. The monolithic growth integration, which actually the growing the epitaxially, the 3-5 materials directly on the silicon. It's mainly on the research study. There are very good results achieved in scientific papers, but still they are not industrially applicable. But all of these solutions, A, B, C, D, and E, are achievable by different process and provided by different integrated photonic vendors in silicon. So it's done, and you can see the main parameters in order to understand what are the penalties related to the different technologies. So if you are looking for the conventional laser isolator fiber peak, or hybrid 2.5 D integration with free space optics, the coupling loss is higher than 2 dB. It can be about 3 dB. So we are losing the half of power of the laser at the connection. The same is also with hybrid 2.5 integration from laser to the peak with the photonic wire bonding. So the related losses are very high. But with advanced coupling technologies, you can significantly reduce the losses related to the coupling by direct attachment of the laser to the peak, or by direct growing of epitaxial structures on the silicon material. So it's very, very important, and it's considered one of the big challenges of the industry, because if you can reduce the losses, the coupling losses of the light source to the peak, it's very, very important. Also, the packaging issues are very important. The stability, reliability, also very, very important for the mass production. So actually, these are the main challenges that the industry face with the integration of the laser. But fortunately, during 2 or 3 years, there are a lot of achievements in the field, and a lot of foundries offering very advanced coupling process, reducing the coupling losses, improving the reliability, improving the yield of the connection, because the yield also important, because in some cases maybe you have a very good technique for the laser attachment to the peak, but in some cases it can reduce the yield near the 50%. So it directly affects on the cost and on the reliability of the process. Okay, so what are the main platforms for the integrated photonics? Indium phosphide, silicon photonics, and silicon nitride. And before you are going to choose the right technology and right platform for your solution, you have to understand what you want to achieve, because all of them has advantages and disadvantages. For example, if you are looking for the solution in the field of data center for the high data rate connection, there are solutions called EMLs, externally modulated lasers. So, for example, for EML solutions, the best platform is using the indium phosphide, because you can use the laser on the indium, you can use the external modulator based on the front scale dish effect, and you can also create the very efficient photodiode on this. What is the problem? If you want to use, for example, the indium phosphide platform for the all-optical signal processing, let's say you want to implement some kind of delay lines or filters, the footprint will be huge. It directly will increase the cost and the complexity of the solution. So in some cases, indium phosphide can be considered as a best platform for your solution, but in some cases it can be not completely not appropriate solution for you. The silicon photonics, you can reduce the cost very, very significantly. There are a lot of devices available on the silicon platforms. The main constraint of the silicon photonic platform is the integration of the laser to the photonic integrated circuit, and in addition, the losses. There are losses related to the modulators. As I mentioned, the typical loss at the modulator is about 5-6 dB. You have the coupling losses, etc. I will show you the link budget analysis in order to give you the better understanding. So it's really challenging. And silicon nitride, what is the main advantage of the silicon nitride? You have very, very low losses. But the main disadvantage that you cannot create any active component of silicon nitride, no modulators, just thermal modulators, and you cannot do much with these modulators. It's very low modulation rates. You should use the external light source, but they are very good platform for quantum computation. They are also very good platform, for example, for the radio over fiber solutions, or for the beamformers, because if you want to use the photonic technology for the beamforming, just as a array of the delay lines, the losses in the silicon becomes very important. So we want to decrease these related losses. So silicon nitride is a very good solution. Silicon nitride also very, very good solution for some biological sensors. So there are advantages and disadvantages in each platform, and which kind of platform you have to choose. It depends on your application. So what are the skills required for the design of integrated photonics circuits? First of all, better understanding in very details the system level requirements. After this, how to translate the system level requirements to the integrated photonic system requirements by means of the devices, link budget analysis, noises, etc., and all limitations. Understanding of the process itself, the issues related to the stability, to the packaging, etc. I will show the entire flow chain from the idea to the production and what should be considered before you are choosing this kind of platforms or solutions. So if you are looking for the density of the integration, and you can see that the number of photonic components increase very fast. Today, we can achieve thousands of devices in the integrated photonic circuits, and very soon we will achieve more. Why it is required? When you are talking about the applications such as neural networks or accelerators for neural networks and deep learnings, you need a lot of devices. So this new technologies requires the high level of integration, and fortunately, we are achieving these requirements of high dense integrated photonic circuits. You can see the comparison between the indium phosphide and silicon monolithic, and also the heterogeneous, where we are integrating different technologies, indium phosphide and silicon together. You can develop the modulator with the 3.5 semiconductor indium phosphide. You can develop also semiconductor optical amplifier for the amplification of the light, and the heterogeneous integration. It means that you can use the silicon platform with the silicon filters and other devices, and you can integrate those active elements from indium phosphide with silicon. But the good news that the number of devices increase. Now I will focus on some application. Silicon photonics based light detection and ranging LIDAR. There are different technologies from the optical phased arrays, which was actually introduced more than 40 years ago, because mostly today leaders are using the moving parts, the mechanical parts, in order to coverage 360 degrees. The problem with these moving parts is the cost. So the integrated solution based on the silicon, it can reduce the related cost and the reliability of those leaders. And there are a lot of companies working in the field, even in Israel. Okay, as you can see, the progress in the field from the optical phased arrays to the most advanced leaders, frequency modulated continuous wave leaders on the chip. So all this is achievable using the integrated photonics. So this is one of the applications of the integrated photonics and what can be done with the integrated photonics. The next application, it's a very important application. It's so-called co-package optics. What is the co-package optics? Today, most transceivers are pluggable devices, but very soon we will want to connect the chip to chip directly without the pluggable devices in order to decrease the footprint and decrease the power consumption. Let's say you have some CPUs and GPUs and you want to connect them directly with high-speed buses. So these high-speed buses can be achieved by the optical communication, but you cannot consider the pluggable devices, which is relatively very big, in order to connect the chips. So co-package optics, this is a solution when you are directly connecting the IOs from one electrical chip to the other electrical chip. In this case, mostly will be used external lasers. Why external lasers? Because the laser is a less reliable part in the optical communication. More than 80% of problems are coming from the laser. So if you are connecting several chips for achieving the high performance computation or high performance switching, you cannot use the internal laser, because once you will have the failure of the laser, you have to change the entire system. So it's better to use the external laser. So the link budget analysis shows that you have at least half dB losses for the connection, and another half dB to the chip, and another approximately 1.6 dB on the edge coupling. And if you are going to the entire link, you will see that the optical loss is about 21.6 dB. It's huge. So if you want to align the standards, and standards are taking some margins, you have the optical power about 25 dBm. It's a laser with their more than 200 milliwatt, and it's not so simple. So the losses are very, very crucial. And if you can reduce the losses by the efficient integration of all components, or reducing the losses related to the modulators and other components, it's very important. Also by increasing the responsivity of the photodiode, because if the responsivity of the photodiode also very low, that means that the conversion is not efficient from optical to electrical domain. So it's also introduce the additional losses. This is the slide from NTT. They are promoting innovative optical and wireless network for 5G, and let's say mostly for the 6G solution. So they are talking about all photonic networks, replacing all functionalities from the electrical functionalities to the optical functionalities. How it makes sense? It makes sense because if you are comparing the optical devices to the single transistor, the dimensions of the single transistor is about tens of nanometers. As I demonstrated, the dimensions of an optical modulator is at least tens of micrometers. So how it makes sense? It makes sense if you are doing operations at high data rates, and you are not doing it at every point of the system. So if you want to use optical signal processing for the filtering purposes in order to improve the quality of the signal, you can do it better than electrical components. If you want to convert the wavelength of the signal from one wavelength to another wavelength at high data rates, for the switching purposes or routing purposes, it's better to do in optical domain instead doing it in electrical domain, because doing it electrical domain, it means that you have to receive the power, optical power, you have to convert it to the electrical power, you need DSP, A to Ds, etc. And you need actually resend the same data with the other optical front end at the different wavelength. So it not make sense if you can do it in optical wave, just converting one wavelength to another wavelength. Okay, so as you can see, the optical solutions and the integrated photonic solutions are penetrating in different areas of the technology. Machine learning, and why it is important. If you are looking for the main functionality of the machine learning in the neuron, what you are doing, actually you are calculating some weighted sum, okay? Those weights are coming from the training of the system. You have some bias and activation function. If you are considering CPUs and GPUs, the power consumption of those devices are tens of watts, thousands of watts. But it can be changed, it can be significantly reduced if you are replacing the electrical components to the optical component. Let's say you have 4 ring modulators. As I mentioned, the ring modulators, they have the transfer function which looks the notch. By applying the external voltage, you can change the transparency of the micro ring. So you can change the amplitude of the light. So it's the same as a multiplication. So if you need to multiply the light, you can do it with the cascaded micro rings. The latency, almost zero, because here you need to use a lot of silicon for the multiplexing of the vector by the vector or the matrix by the matrix. In this case, the main latency is the propagation of the light in this small device. It's almost zero. So it can significantly reduce the latency. You can significantly reduce the power consumption. So you can implement the integrated photonics for the machine learning and deep neural networks. These are some examples. This is the deep neural network implemented by MIT. This is for vowel recognition. If you are looking inside you have the so-called cascaded unbalanced Mach-Zehnder interferometers for the purpose of the vector-to-vector and matrix-to-matrix multiplication. So these kind of applications can significantly reduce the power consumption of GPUs and CPUs. I'm not saying that you can completely remove the needs in CPU and GPU, but you can use those integrated photonic circuit as an accelerators for these technologies and these requirements. So, okay, now we have an understanding what are the main components, what are the main challenges, what we can do with the integrated photonics, what is the process. So the process starts with the system concept. What is the concept of your system? What is your application? Once you have the concept and good understanding of your system, you should transform it to the optical architecture. Okay, I have a requirement on the system. I know what is the functionality of the system. I should convert these requirements to the optical architecture. In this case, it's just the laser, it's just the Mach-Zehnder modulator and the AWG. For example, this is the example for the WDM optical communication. Okay, I have an architecture. What are the building blocks? What are the system level requirements and how I can achieve these system level requirements by the building blocks? If I have enough bandwidth, if I have not a problem with the link budget by means of the power, by means of the noise, by means of the integration, etc. Okay, so now you have find the right building blocks for your system. The next level is the circuit design and layout. You have to put everything together, connect them, and run some simulation in order to understand that your system has a good potential to meet your system level requirements. If you have some problems, you can figure out them on the initial stage of the circuit level modulation, and you can improve it by design or by replacing some or improving some building blocks. Okay, the next is the manufacturing part, where you're sending your so-called GDS to the vendor. After this, you will receive your chips, chip characterization, and packaging. But I want to be very clear here in this point. Are always going from 1 to 7, but don't consider it in this way. because you are giving the feedbacks at each level. Because I'm never sending my GDS file for the photonic integrated circuit to the manufacturer before I am closing the issues related to the packaging and test. It's very nice if you will have the photonic integrated circuit, but it does not mean that you can easily package or test them. So before you are going to the manufacturer, you are sending your GDS file, you have continuously in backward propagation, check every details. If you want to package the device and you have a limitation of the bandwidth or requirement of the bandwidth, electrical bandwidth, are your pads designed in the right way? What are the packaging methods? Should you use the wire bonding or flip chip? It depends on the requirements, and you cannot complete this process if you are not doing the back analysis and you have a good understanding of all limitations. Otherwise, this is the most characteristic for almost all startups in the field of integrated photonics. They are mainly spin-offs from the academy. They are doing very well the photonic integrated circuit, and once they are going to the manufacturability, to the testing and packaging, oops, we have a problem. We cannot do it. So my recommendation, if you are looking for this kind of solutions, you have to understand all process all together before going to the manufacturing. This is actually the same demonstration of the same idea on the timeline. Okay, so I will not spend a lot of time on this slide. How we can design the integrated photonic circuits? There are a lot of tools, and they are improving continuously. One of them is the Lucida IPKIS. This is a Belgian company. This is a spin-off from IMEC. They have a very helpful tool for the design of the integrated photonics. They are supporting the most PDKs. PDK is a process design components that you have from the different vendors. So they are supporting most of them. They have a different approach. It's mainly based on the Python programming. Instead, other tools that they are mostly based on the like a Simulink, the block-based designs, but this is very important, very helpful tools. I am using this one. Virtual photonic instruments, they are working on the market more than 3 decades. They start as solutions for the network level and the system level, and today they are penetrating to the component level. They have very good tools for the quantum key distribution, quantum communication, and quantum computation. Also, other tools are numerical, which was acquired by ANSYS. You can do a lot with numerical from the device level up to the system level, thermal simulations, electrical simulations, everything what you want to do. RSoft was acquired by Synopsys. Also, this is the part of the Synopsys. You can do a lot from the device level up to the system level, including all types of simulations. You can use different tools from the Synopsys for the optical simulation, for the electrical simulation, for the circuit simulation, including thermal simulations, etc. So the tools are very, very advanced tools. This was not a situation 10 years ago. 10 years ago, those tools are some standalone tools. we are not integrated in the big platforms, like ANSYS or Synopsys. So it was just for the research and development purposes, not for the real industrial solutions. But today, fortunately, this situation is completely different. Okay, so you understand the process. You have a tools to design your integrated photonic circuit. What is the next step? Well, the next step that most companies in the field are the fabless companies. So you are looking for the foundries for the manufacturing, for the fabrication of your devices, and there are a lot of them. A lot of them, it's different on different platforms. CMOS, it can be QMEC in China, IHP, Germany company, VTT from Finland, IMEC from Belgium, Global Foundry, Tower Jazz, Industrial Fabs, AMF is from Singapore, Lynex is from Holland. You have also STM, TSMC, but TSMC, they have not the open platform. Actually, they are doing silicon photonics, but they are not providing PDK, so you cannot really do nothing with the TSMC, especially if you are a small player. And also there are some service providers, VLC from Spain. They can help you in the development, in the packaging and testing of devices. So the main players are here. You can see the standard silicon photonic process. It's from QMEC. You have silicon substrate. You have germanium for the photodiodes. So you can see the P++ contacts and N++ contacts to the photodiode. Those are the metal layers. You can see here the PN junction for the modulation purposes. They are even provided some silicon nitride solutions because, as I mentioned, you have less losses in silicon nitride. So if you have a huge photonic integrated circuit and you have the very long waveguides, you can go to from silicon to the silicon nitride and use the silicon nitride for the long connection in order to reduce the losses. So there are a lot of possibilities how to fabricate your photonic integrated circuit. Okay, once you have photonic integrated circuit, definitely you want to somehow integrate with some electronics because the most foundries, they are not providing the solutions also for the electronic circuit. Just Global Foundry has a solutions for the integration of photonic and electrical devices, but it's 45 nanometer process, so you cannot achieve a lot with this. Just if you have some analog devices like drivers for the modulators or transimpedance amplifiers, you can do it in same process. IMEC, QMEC, AMF, Tower Jazz, they are not providing the solutions for the integration of electronics and the photonics. So we have the side-by-side wire bonding. It's very simple, but it's very limiting because if you need the very high-speed connection, the length of the wire bond with the main constraint for your bandwidth. So you need to understand what are the parasitic capacitance and what you can do with this wire bond, what is the right shape and right length of this wire bonding based on the requirements you have on the bandwidth, band reflections, etc. So you need some co-simulation of your photonic circuit with the electronic chip. You can use also the interposers. You can connect the photonic chips via the interposers. There are some ceramic interposers or organic interposers. Before you are considering to use the interposers, you should understand that you have to develop those interposers, find the right partner for these interposers. and they are adding significant cost to the solution. Okay, flip chip also can be considered. You just can flip your photonic circuit on the electrical circuit. It also needs some understanding how to do it, what kind of materials you are using for bowling and bonding. It's also not so easy. I'm not saying that it's impossible, but you need to understand very well what you are doing before you are deciding that you are going to the flip chip solution. There are also some other mostly nice solutions as true silicon vias. For example, Tower just provide this kind, so we can use the true silicon vias, and at the upper side you will have the photonic circuit, and the lower side, you will have electronic circuit and monolithic front-end integration, as I mentioned, Global Foundry is doing. And you have the comprehensive analysis of advantages, of disadvantages of each of them. So depends on the solution you are looking for. And before you are going to design and to send your GDS to the foundry for PIC, you have to understand the entire solution, the entire limitations you have, otherwise you cannot achieve your development goals. Okay, now I will very briefly introduce the New Photonics. I am also CTO of New Photonics. New Photonics was established 3 years ago by Yaniv Ben Chaim and Yossi Zilberfarb with the huge experience in the field of semiconductors, in communication, etc. So I will not take a lot of time from this. And what we are bringing to the market, what is our solution? As I mentioned, the conventional solution from the I/O, from the transceivers, this is a transceiver, is based on DSP. It's actually not DSP. It's not the programmable digital signal processor. It's mostly dedicated signal processor with very limited functions. And analog front end and optical transport is actually transmitter and receiver in optical domain. This DSP costs a lot, and the power consumption of this one is more than 60–70% of the entire power consumption of the devices. In order to develop efficient DSPs, Broadcom, Marvell, MaxLinear, and Credo, they are using cutting-edge technologies, 3–5 nanometer technologies. It's very long way to develop this kind of devices, and the tape-outs are also cost a lot, more than $25 million per tape-out. So it's not a solution for the future requirement. So our concept is actually to replace this DSP by all optical signal processing. How we are doing it? We are using the modular lasers. Modular lasers, actually, they are comb lasers in frequency domain, and in time domain, they are creating very narrow pulses, 1 picosecond with the high repetition rate, 20 picosecond. These devices, semiconductor device, a semiconductor optical amplifier, semiconductor based laser, very small. The operational current is about 250 milliamp with 3 volts. So the entire power consumption is less than 1 watt. And we can do with this device a lot of things. I will demonstrate some movies and some demos, live demos. This is another comb laser we have developed at New Photonics based on microcomb, a silicon nitride solution. In this case, we can create hundreds of modes. And also the time domain, this is the pulse train, very short pulses. We can create 100 gigahertz, 150, 200 gigahertz pulse train in order to transmit high data rates. And I will just show the demo, real-time demo. Just a moment. I want to demonstrate the photonics optical cell. Surface is serializer and deserializer. You can see that we are using Credo board. We are using 112 gigabit per second lines. Those lines are launched to new Photonics demo box transceiver. This transceiver combines two 112 gigabit per second channels in order to create one combined 224 gigabit per second channel. I will demonstrate how we are creating this combined channel. What you can see on the scope that the data is transmitted by the time pulses. The width of each pulse is about 1 picosecond, and distance between them is about 20 picosecond. This is a single channel. Now I can show you how we are creating the combined high data rate channel. Okay, it's enough. Actually, you can see that now we have additional second channel. I chose different powers in order to distinguish the difference between the channels. The time between those pulses is 20 picosecond, and the time between the neighboring pulses is 10 picosecond. Finally, they are creating 100 gigahertz, 100 gigabaud pulse train in time domain. Actually, using pump form signal, we can transmit 200 gigabit per second using this combined line. So this combined 100 gigabaud per second channel from the transmitter is transmitted via the 2-kilometer fiber to our receiver. I want to show you the receiver side of our all-optical service. As I mentioned, we have combined two 112 gigabit per second channels in order to achieve 224 gigabit per second combined channel on the single lane. Now we are multiplexing those channels, and you can see one of them, and you can see also the performance of the receiver. Okay, I will skip this one. This is the second channel. So what we are doing, instead using this DSP, as I mentioned, this dedicated signal processor, which is mainly used for the gearboxing of the channels in the electrical domain by the retiming by A to D, and it's cost a lot by means of the power and the complexity. We are doing it using our modular laser, using so-called time division multiplexing with a single light source without any DSP, and the other components, they are mostly passive components, so the power consumption is significantly reduced. And now I will also show you another demo. This was demonstrated in Glasgow during the last ECOC. We have achieved together with Intel very high data rate, 224 gigabit per second transmission per lane without any DSP. Without any DSP, that means that we have significantly reduced the latency, the cost, and the power consumption of the solutions.
As I say, one of the best things to the last. Many of you have seen that this ECOC was the year of 200 gig per line. Many of you have seen many press releases, but some of you saw that Intel is working with a new company called New Photonics. New Photonics and Intel together, they announced 224 gigabit per second per line, direct modulation, PAM4, without DSP, over 10 kilometers using a 224 gig circuits from Intel. When you see these numbers, I must say, last OFC, you rocked the world with a big announcement working together with Credo. But this year, you don't need a DSP. What are you bringing?
Okay, good morning, everyone. What we are demonstrating today is actually 224 gigabit per second transmission or 12 kilometer of fiber. The signal is coming from the service which is provided by Intel. It's a service with 225 4 gigabit per second lane bound for signal. The signal is launched to our transceiver. We are using optical signal processing in order to mitigate the channel impairments, and the result is that we are transmitting this channel with very good results. You can skip it.
Okay, so I will skip it. The major players in the field of the silicon photonics and integrated photonics are shown in this slide: Cisco, Intel, MACOM, Global Foundry, Luminar, Marvell, Coherent, IBM, STM Microelectronics, NKT Photonics, Ranus, and a lot of them, Requi, Broadcom, Hamamatsu, Effect Photonics from Holland, Fujitsu from Japan, Hamamatsu also. So there are NVIDIA, Mellanox, Sequoia from Germany. So there are a lot of players in the field because, as I mentioned, the field is growing. It's considered the next breakthrough in the technology, and it's actually reshaping the world of the data communication, and not just the communication, also other related fields. So this is a conclusion. So now, if you have questions, I am ready for your questions.
I know that it is too late, so one or two quick questions, please. I have a question for you.
No problem at all.
Do you think that in the future there will be a catalog of components like in electronics?
Actually, there are several players in the field, and most of them are providing so-called libraries. So there are standard devices from libraries. You can use them as is, but you can also improve the performance, the characteristics of devices. So for example, if you're going to IMEC, they are providing you a lot of library components. Yeah. If you are going to the Global Foundry, they are providing the process, but related very small number of library devices. So there are different solutions. It depends on your positioning in the field, what you are doing, what your expertise, and what is your readiness in the field. But yes, definitely they are improving and increasing the library components in order to accelerate the process, because it's a win-win. If you can easily design your solution, you go to the foundry. And actually, this is the business model. Yeah. So yeah, they are improving the libraries. You can definitely use the existing components, but sometimes you have to develop your own component on your own demand.
And about the metrology companies, are they ready for testing in mass production of these devices?
Yeah, there are some companies, they have so-called wafer level testings. So yes, there are some solutions, but when you're considering the mass production, you need to take some things in the account at the design level, how to design your components and your system in the right way in order to be ready for the wafer level testing. If you will not consider it at the initial stage of your design, you will not be able to do it by means of the coupling, etc. So you have to discuss these testing issues with those service providers. Otherwise, you will find yourself that you have a very good peak without the capability of the fiber level, wafer level testing. But there are a lot of players, they are providing these kind of services.
Okay. Any other wants to provide to give a quick question?
I have a question. I'm Uzorion. Thank you very much for your enlightening lecture. It was very, very interesting. The question is, the optical communication is clear that the future is in high rate optical communication. About the optical processing, do you think that we shall have some products for the near future optical processing?
I think definitely yes. I have not demonstrated to you, but in New Photonics, we have developed some programmable filters, and we are improving the impairments of the optical link. We are working also for the solutions for the matrix multiplication, and you can check light matter. 2 weeks ago, they received more than $125 million investment from Google to improve the connectivity for neural networks and also for the computation. So yeah, the field is changing every day. And I think that in very near future you will see the photonics not just for the communication as the fast couriers, also for the processing. The main challenge for those complicated systems is the capability of the calibration and monitoring. So we have a very unique solution for the calibration and monitoring of the complex photonic systems. So yes, definitely, I believe that in 2-3 years from now, maximum, we can see the photonic solutions also in the field of signal processing for the acceleration of neural networks, encryption, etc.
Okay, I would like to thank you. More questions?
No, thank you very much.
Okay, thank you very much, Professor Ben Ezra. It was very interesting lecture, and we hope to see you sometimes in the coming future.
Okay, no problem at all.
Right.
Thank you.
Thank you. Thank you all.
Thank you. Bye-bye.